I know that things in the world are pretty challenging. There's a lot going on with the transmission grid, a lot of anxiety over the fact that we expect to see about a 40% increase in demand over the next 20 or 30 years to accommodate the decarbonization. A lot of incentives in play right now. It's nice to see that the administration is supporting investment in progress. Let me see if I can get the slides to roll here. Here we go. Well, it's pretty obvious when we start having freezing temperatures in Texas and triple-digit temperatures in Canada that there maybe be some actual truth to this climate change thing, and that is putting a lot of stress on the existing grid. So I'd like to talk today a little bit about how we can use modern conductors to actually improve the efficiency, capacity, reliability, and resilience of the grid. I know there are things that cause us to stay awake at night, and making bad decisions is one of the top things. And considering that there's so many failures that cause so much difficulty with the grid, blackouts and other things, due to just 100-year-old technology, it seems the time has really come to start leveraging modern technology to start to chip away at some of these problems that have such devastating consequences. You may recall that the major East Coast blackout in 2003 was caused by telemetry device failures, computer glitches and reboot failures, poor communications between the grid operators, and ultimately that led to excessive conductor sag that caused a cascading blackout. And blackouts are not fun. It's inconvenient when you can't use your computer or communicate. It's inconvenient when you can't see. It's probably terrifying for people that get stuck in elevators, although I think sometimes the population grows over things like that. But it also impacts economies. Even small businesses like restaurants can lose thousands of dollars in produce. So we take the ramifications of power outages very seriously. In particular, over the last 10 years, the drier climate, drought conditions, strong winds, and climate change have really caused huge problems with fires in the whole Western United States and other parts of the world. So doing what we can to reduce the risk of conductor failures and sagging conductors to minimize these types of occurrences is a really important thing. We're working hard to tackle that. We've been working with Southern California Edison, and here in California, they've been doing a lot of reconductoring, taking down existing ACSR conductors and even some ACSS high capacity conductors to minimize that thermal sag. And also, as I'm going to talk about in a few minutes, the ability to carry twice the current over existing transmission structures can help us really meet the decarbonization goals, deliver more power, deal with changing load flow conditions, and even reduce line losses. So those are some of the highlights that I'm going to get into here shortly. For those of you that are not familiar with ACCC conductor, it uses a hybrid carbon core. It's quite a bit lighter than steel. It's quite a bit stronger than steel. But most importantly, it has a very low coefficient of thermal expansion that mitigates thermal sag. As I'm sure many of you are aware, when you increase current in a conductor, the electrical resistance causes them to heat up, which results in conductor sag. So being able to mitigate that conductor sag allows you to carry much more current, especially when you're in an N-1 condition where you've got a planned or an unplanned outages, or in a case of fire where grid operators can have the opportunity to actually reroute power around high-risk fire zones or active fire zones. So those are very important advantages. And while today I want to focus mostly on reliability and resilience, I have to give a call out to the efficiency folks, because the ability to reduce line losses by 30% or more has huge ramifications and help us reach our carbon emission goals. And it's an important thing. I'm going to touch on that a little bit also. Bottom line with this product is that it resists corrosion and cyclic load fatigue. It's produced to ASTM standards, so it's a very consistent in quality. It's currently manufactured by 35 conductor manufacturers worldwide. There are 11 hardware manufacturers that we also work with to deliver the product to various places around the world. And we've completed over 1,000 projects in the craziest environments that you can imagine: mountain ranges in China, deserts of Qatar. My friend Joe Sylvia, who's on the line, he can talk about doing installations in Siberia. So we've learned a lot of things in the field during installations, and I think in terms of reliability, especially as you're exploring new technologies, it's really good to have that experience base to help you plan for and avoid things that can happen during installations of any type of conductor. This is a picture taken from a test protocol that AEP performed about, I think it's probably been 8 or 9 years. They did a sequential mechanical test where they subjected conductor samples to 100 million cycles of vibration, 100,000 cycles of galloping, and then they did a series of tensile tests, and then post-mortem tests after the fact. But I think one of the most important things for reliability in terms of overhead conductors is that many of them experience cyclic load fatigue, or in the case of the picture here in the ACSS conductor, you have fretting fatigue because the vibration causes the small contact point to rub back and forth against each other, which then causes microfractures to propagate and conductor to the strands to actually break, which can then lead to conductor overheating and then ultimate failure of any type of core. So the smooth surfaces of the ACCC conductor combined with the smooth surface of the trapezoidal strand helps mitigate the cyclic load fatigue in aeolated vibration. So it really helps. That helps with reliability. This is just a basic comparison chart from a brochure that shows the ampacity capability of ACCC compared to conventional conductors like ACSR and AAAC. The key point here is that in terms of the added capacity, not everybody's going to run these things at double capacity all the time, but having the ability to crank the amps up to 200 degrees or even higher really can help you get through a situation where you've got otherwise overloaded and sagging conductors. And there have been dozens and dozens of blackouts that have been caused by sag trip outages over the years all over the country and worse. So the high capacity can help with the reliability as well as just delivering power. This is a comparison that was done by Hydro One up at Kinetrix Lab. They ran different conductor types and they compared them to the ACSR conductor, and they ran 1,600 amps through different Drake size conductors of different designs. And you can see the ACSR conductor sagged pretty substantially, but the reality is that conductor and the sag would have been set at some lower level. Most people operate ACSR conductor maybe around 75 degrees C with excursions maybe to 100, or some utilities even take it to 120 or more. Although hardware isn't really designed to go to those levels, so you have to be very careful about running ACSR conductor hot. Now, the conductors over in this yellow highlighted box, they're actually designed to be high temperature, low sag conductors. But assuming this was a reconductor project, being able to upgrade the capacity of the ACSR conductor with some of the other high temperature, low sag conductors may not give you a 2x increase in ampacity. You may see a 50% increase, because what will happen is those conductors also exhibit fairly substantial sag characteristics that would limit the ability to double the capacity for those N-1 conditions. If you look up at the green and the blue lines, you'll see these are gap and ACCC conductors that both beat that sag criteria. The interesting thing, however, in the same group of HTLS conductors, in this case, the ACCC conductor ran 60 to 80 degrees C cooler than the other HTLS conductors. And that sort of underscores the improved efficiency. And as you, I'm sure, are aware, I²R losses can be pretty substantial when you're running hot. And to be able to, under really any load condition, operate cooler really helps with improve the efficiency and the capacity. So that's a big plus. most of I've been with CTC now for 19 years, and most of the projects that we've done have been reconductor projects. Although there have been a lot of more and more rebuild projects to harden the grid, and then we've probably done somewhere in the neighborhood of 75 or 100 new transmission lines using this product, because it's lower sag and higher strength allows increased spans between fewer or shorter structures, and that can really help with the economics, and also minimize some environmental exposure when you've got challenging conditions, and it can reduce time frame. So these are some examples of the types of projects that we've done. Just quickly, and as the company has matured and we've learned more about how we can help utilities solve their problems, we've introduced some variations on the theme. The ACCC conductor consists of about 50% carbon and 50% glass fiber. We use a glass fiber to improve the flexibility and toughness, but most importantly, the glass fiber provides a galvanic barrier between the carbon fiber and the aluminum. You cannot have carbon fiber and aluminum in substantial and direct physical contact in the presence of an electrolyte like rainwater or agricultural pollution or anything like that. So the glass core on the ACCC conductor is hugely important in terms of reliability and longevity. The ULS conductor actually uses a higher grade carbon, and the ratio of the carbon to the glass is increased from 50-50 to 70-30. So it's got a higher modulus, a higher strength. It's about twice as strong as HS 285, if you're familiar with the product, the high strength steel. So it's quite a bit stronger than high strength steel. And again, it's about 70 or 80% lighter, which again allows us to use trapezoidal wire to get more amps through those wires. Also to mitigate extreme ice load conditions or the 2-mile river spans, we've developed the AZR, which is essentially just a plain ACCC or a ULS core that has aluminum zirconium alloy to give the conductor additional strength. We normally use fully annealed aluminum. It has a ICAS rating of 63% of copper, annealed copper. The AZR drops it down to about 60%, but you get a lot more strength and only giving up a little bit of the efficiency aspect. These are some project examples. As I mentioned, we've done installations in 60 countries or more so far. We currently have about 45 projects that are active and about 70 more projects that are in the queue with start dates between now and the next 4 or 5 months. So it's taken off. About 250 utilities worldwide have decided that this is really good stuff. And I encourage you, if you're not familiar with it, to take a closer look and let me know how we can help you. We've got a conductor comparison program that will help you analyze, and you can just go to our website, and there's no charge to use it. You can create your own account and do conductor comparisons. That can really help reduce project cost, optimize conductor selection, and give you some of these advantages with very little difficulty. I think it's important that testing be performed. Now, while we learn a lot of stuff out in the field, again, at over 1,000 projects, the importance of doing performance and longevity testing in the lab cannot be understated. And there are actually standards that have been developed for these particular tests, as well as for the development of composite core conductors. ASTM B987 is the baseline for that, and it's a good idea to take a look at that when you're looking at conductor selection, and we'd be happy to help you get through that process when if you become interested. This is a visual that sort of that shows when it relates to reducing fire risk or surviving severe fires. A lot of studies have been done, and it shows that the sag of a conventional conductor can actually get into the flame zone where temperatures can reach 400, 500, 600 degrees C, really get hot. So to be able to A, handle those high temperatures, but B, stay as far away from them as possible, can really help improve reliability and prevent fires. So that's a very important aspect of what we're doing, especially in the Western United States. This was a picture taken by SSEN in Scotland. They did a reconductor project. It was about a 45-kilometer reconductor project. They used 95% of the existing structures, and they replaced ACSR with ACCC. And you can see the pretty dramatic decrease in sag. They doubled line capacity, or actually got 2.5 times the capacity, and they mitigated the sag. So they were quite happy that they could use the existing structures. They were very happy that they could deliver more power to accommodate growing industrial demand in this particular region. And it was pretty much a home run. They actually won an award for their project in Scotland. Sometimes bad things happen. This is a picture that was sent to me by Jim Lehan at NV Energy. He had recently, this is going back to 2012 or so, he had recently installed a very small ACCC Lynette size conductor to replace a 4-aught copper conductor on these old wood frames, wood H frames. At the time they installed the new conductor, they were able to do this under a maintenance program, and this was good because they had to cross BLM land and private land and all that stuff. So they reduced the permitting issues. They used steel cross arms, new insulators, and the ACCC conductor. The ability to increase capacity on this allowed them to shut down spinning reserve down in Carson City. This line went from Reno up in the north down to Carson City, the capital of Nevada. And so they were able to save $9 million by shutting down a spinning reserve by increasing the capacity of this line. Now, this line was out of service for 4 days because of the fire, but fortunately the conductor wasn't damaged. They were able to come in, replace the wood uprights, use a helicopter, replace the insulator, and lift the conductor back in service. So the fact that they could get the line back in service quickly is really sort of underscored an example of resilience. And again, as we think about reliability, we also have to think about there's no such thing as bulletproof, there's bullet resistant. And when it comes to resilience, you want to get things back in service as quickly as possible. This picture shows damage that happened to the conductor strands after being hit directly by an EF5 tornado in Moore, Oklahoma. I think winds in this zone were measured at about 220 miles an hour. This was a new line running north-south from a generation facility that was just to about a half a mile south of where this picture was taken. They mounted this on steel monopoles about 125 feet above grade. An oil tank was picked up by the wind, slammed into a steel monopole, knocked the thing over to about 45 degrees. And the shock wave actually caused these fully annealed aluminum strands to snap. The good news is that the core that's relatively elastic, could take the shock wave without breaking or being damaged, held the conductor in the air, which allowed 4 guys and 2 bucket trucks to get up, splice in a 20-foot piece of conductor in 4 hours, and run down the road and deal with other problems, because that was a pretty severe hit that they took in Moore, Oklahoma, back in around 2013. So this is just another example of how you can leverage technology to improve reliability and resilience. One of the most sometimes overlooked but hugely important characteristic of the system, the conductor system, is the hardware. You may have recalled from about the second or the third slide, it talked about different types of conductor failure modes that included about 50% conductor and about 25 or 30% hardware problems. One of the common things that can happen with dead ends and splices is that aeolian vibration can cause strand fretting and breaking. You can break the strands, and that could cause overheating. Also, most dead ends and splices were designed, they're fairly compact, and they don't have a lot of additional aluminum content. So these devices can heat up when the conductors are running hot. And the oxidation inhibitors that were used for ACSR conductor in particular really weren't able to handle high temperatures. So while some utilities will operate ACSR conductor, carry more amps on a hot day, and the temperatures might get hotter, there have been a number of problems with overheating of dead ends and splices. Now, in terms of the composite core versus the steel core, with the steel core, you can squeeze it with a 60-ton press or 100-ton press, and essentially you'll squeeze down on the typically seven strands in an ACSR, ACSS conductor, and they will plastically deform. So when you try to squeeze them tight, they will just change their shape and turn into like trap wires because you're squeezing down hard on them. And that's just fine, because the strain limit of steel is about 1%, and it can handle that, but it will plastically deform. With composite cores, they do not plastically deform. And if you don't grip them correctly, you can cause damage. And this Collet system, there are about 1 million of these things in service going back to 2004. The Collet system actually provides a very strong grip on a very small core, and it allows elongation at the entrance of this where you would otherwise see stress concentration. So near the picture of the crescent wrench where you see the composite core entering this Collet assembly, that can be a problematic area. So this thing was designed very well in stainless steel to be able to clamp down, grip the core, but not cause excessive stress where the core enters the Collet system. And while I know that a number of new conductor manufacturers have begun understanding that carbon fiber is really a superior choice for overhead conductors because of its lightweight and high strength and resistance to cyclic load fatigue and resistance to corrosion, a lot of good things. I encourage them to spend a little extra time sorting out their hardware so that they don't have conductor failures due to bad hardware. So there's a lot of background about that. I'd be happy to share with anyone offline if they're interested. We do use standard tools and equipment. There are installation guidelines that will advise people what size sheave diameter wheel to use and things like that, and how to pull around 90-degree angles. Very important if you're thinking about reliability. You want to make sure that you install these products, whatever type of conductor or product is. You want to follow manufacturer's guidelines and do a good job of installation. Because the composite core is smooth and the trap wires are smooth, and when you use a Chicago grip or a sock to help pull in or hold the wire, you're really only grabbing the outer aluminum, and you're counting on the aluminum to squeeze down and grip the core. So to prevent slipping on really long spans, we've designed a thing called a bug. In the bottom right, you can see a picture of a little device that you screw down on these things on the core to prevent slipping. So that can help with when you're doing river crossings in particular. It's very helpful when you're dealing with people that have different backgrounds and speak different languages. Being able to help educate them using training videos is very solid. You can see some examples of training videos on our website when you get to that stage. We do follow IEEE 524 guidelines during installation. We use, as I mentioned earlier, we use conventional tools and equipment. We do have guidelines about what not to do. It's not a good idea to drag the conductor over fences, for instance. You want to use proper care. That's no problem. One of the benefits of our experience is that we've got 48 master installers that travel around the world to help train crews and show them correct practices, make sure they're doing things safely and wisely. So that's important. And I think that as we look towards the future, we're thinking about what the possibilities can be using information technology, and our starting point for this was we embed fiber optics in the ACCC core, and that allows the lineman to send signals through the core after or during installation to make sure that something didn't happen. Again, we're doing some of our pulls have been 8 reels back to back at a time over a mountain range, and you can't have a lineman standing there looking at every single sheave wheel. So we've developed a system to inspect the core to make sure that there was no excessive bending or other damage that can sometimes occur to conductors while during installation. So it's a very effective device, very easy to use. There's no cost to utilities to use it. We do have master installers that have the equipment, and they're deployed to wherever needed. But it adds a level of confidence that I think is worth considering if you're looking at modern conductors. We've had a lot of successes. This is a picture of some of our friends down at American Electric Power that did a 240 circuit mile reconductor project on a 345 kV line while it was energized down in South Texas. They finished it, I think, in 2016 or so. So it's a little bit old. But what was most remarkable is that they did this project using reconductor with ACCC to essentially double line capacity to serve load growth. In the winter, they've got a lot of snowbirds that go down to South Texas to stay a little bit warmer. Everybody uses electricity. Demand goes up during the peak winter and peak summer conditions. And they were very happy that they could use the existing structures. They had so much confidence in ACCC conductor. They ended up doing it with Quanta energized services while the line remained energized, so there was no outages. But what was really interesting after the fact, they realized that their load factor was only 34%. So this is not a highly stressed line. This line is sort of idling nicely along most of the year. But even with a low load factor of 34%, they saved 300,000 megawatt hours per year. That's a lot of savings. And not only did that reduce CO2 emissions by over 200,000 metric tons, which is the same thing as removing 42,000 cars from the road. So these guys want to increase line capacity to deliver more power during peak conditions. They wanted to save money and save outage time by doing live line reconductoring using the existing structures. They won big time. But to be able to reduce the line losses, which also freed up 34 megawatts of generation capacity that was otherwise wasted. So the price of the wire was offset 6 times over by doing this project. And what's happening now is that there are a lot of developing countries that are looking to increase capacity of existing transmission lines. We've got a lot of friends in Bangladesh that are upgrading their system, and they're receiving money from international development banks, and they're actually specifying high capacity energy efficient conductors, because not only does that help them deliver more power, it's helping them meet their sustainability and carbon reduction goals. So it's a big win, and being able to help combat climate change while you're dealing with it is not a bad combination. So that's the extent of my my input for today, and I'd be delighted to handle questions now, or if you want to reach out to me by email or phone, that'd be great too.
From someone, is there excess weight with ACCC compared to ACSR?
No, the composite core is 70% lighter than steel. It allows us to put in 28% more aluminum using compact shaped wires. So the net weight is almost identical. It is slightly less, but virtually identical. If I gave you a conductor that had a large diameter, but it was a lot less weight, you could have blowing winds, and that would give you another problem. So the idea was to meet the diameter, meet the weight, double the capacity, and cut out thermal sag.
Is that part of the reason for the reduction in sag, the less weight?
No, because the conductor itself weighs the same.
Okay.
The finished conductor weighs the same as ACSR or ACSS, but the low coefficient of thermal expansion of the core is virtually zero. Means that when the wire gets really hot because you're carrying a lot of current, the core doesn't move. It doesn't stretch like steel.
Daniel, do high efficiency, low loss cables have a place inside the fence, inside of facilities, or is this strictly for utility use?
This is a utility use. We've done a lot of substation bus bars and things like that, but it's really a transmission and sub-transmission product. We have developed a number of very small diameter conductors that are getting down to distribution levels, but the lowest level that we've gone thus far is about 11 kV. So we do have a smaller product line for what we consider to be high end of distribution or low end of sub-transmission. So there are smaller conductors available as well.
Yeah, that was another question that came up. What are the distribution applications for this?
Somewhat limited. We're still running copper wire from the 240 volt pole in the backyard to our houses, but because we're expecting electrification of cars, we know that we're going to have to be doing a lot better job delivering power with sub-transmission lines, and we're actively doing that today.